A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
My Weird Prompts is a community-driven initiative exploring how AI can fuel curiosity and uncover the fascinating ways our world works. GPU compute for this podcast is generously provided by Modal. Learn more at modal.com.
You know, Herman, I was sitting there yesterday staring at a loading spinner on a simple voice transcription app, and I realized something. That little bouncing circle is the last great barrier between us and a world that actually feels like the future. If I have to wait 500 milliseconds for an AI to realize I have finished a sentence, the magic just dies. It is like trying to have a deep conversation through a walkie-talkie with a 5-second delay. It makes you feel self-conscious, right? You start wondering if the machine is actually thinking, or if the internet just went out.
That delay is the dragon we have been trying to slay for the last 3 years, corn, and honestly, it is the defining engineering challenge of 26. Today's prompt from Daniel is about the engineering war against latency, specifically how we are moving toward real-time multimodal experiences. It is a massive shift. We are moving away from the era where we just bolted a pair of eyes and ears onto a text model and called it a day. We are entering the age of the unified engine.
I remember those early days, and by early days, I mean like last year. It felt like the AI was wearing a headset and looking through a separate camera, then sending all that data to a central brain that had to sort it out. It was clunky. It was slow. And honestly, it made the AI feel like a very polite but very overwhelmed intern. Daniel wants us to dig into why that is changing now, especially with everything that has dropped just this month. We are talking about a fundamental re-architecting of how these models perceive the world.
Herman Poppleberry here, and I have to say, the timing of this prompt is incredible. Just today, March 26th, Google released the TurboQuant framework. We are also coming off the heels of the NVIDIA GTC event where Jensen Huang showed off the Vera Rubin platform. The industry has collectively decided that being smart is no longer enough. You have to be fast. We have shifted from an obsession with flops floating point operations per second to a total focus on TPS, or tokens per second, and TTFT, which is time to first token. We are talking about sub 100 millisecond response times for humans and sub 10 milliseconds for autonomous systems.
Sub 10 milliseconds? That is faster than the blink of an eye. Why do we even need that? I mean, I am a sloth, Herman. I can live with a little lag. But I assume if a self-driving car is trying to decide if a plastic bag is actually a stray dog, 10 milliseconds is the difference between a non-event and a tragedy. Or if a robot surgeon is reacting to a sudden bleed, you do not want it waiting for a cloud API to return a JSON object.
That is a perfect example of where the stakes are highest. But even in casual interaction, there is a concept called the temporal alignment threshold. If the audio and video tokens are misaligned by more than 50 milliseconds, the model starts to lose its grip on what is actually happening. It is like watching a movie where the dubbing is slightly off. It does not just look bad, it breaks the underlying logic of the interaction. If the AI sees you point at a cup but hears you say that 60 milliseconds later, it might not associate the word with the gesture. The reasoning itself degrades because the context is fractured.
So, let us talk about this shift from text-first models to native multimodal architectures. In the old days, which I guess was about 18 months ago, we had these sidecars, right? One model for vision, one for audio, and they all fed into a text-based large language model. We called that late fusion. Why is that falling out of favor?
Because late fusion is fundamentally limited by the bottleneck of the translation layer. If you have a separate vision model describing a scene to a text model, you are losing a massive amount of nuance. The vision model has to decide what is important enough to put into words. It is like trying to describe a sunset to someone over the phone. You can say it is orange and red, but you lose the gradient, the texture of the clouds, the way the light hits the water. An early fusion model, like Gemini 1.5 or the new Qwen 3.5, sees the whole scene as raw data. It converts pixels, sound waves, and text into a unified stream of embeddings from the very beginning.
That sounds like a nightmare for the engineers trying to keep everything in sync. If everything is just a giant soup of embeddings, how do you make sure the AI knows that the loud bang it just heard is connected to the vase it just saw shattering on the floor?
That is the core of the architectural complexity. In an early fusion model, the cross-modal relationships are learned during the initial training. The model is not being told that this sound equals that sight. It is discovering the statistical correlation between them in a single high-dimensional space. The benefit is that the reasoning becomes much more fluid. The downside is that you can no longer optimize the vision part or the audio part in isolation. You have to optimize the entire unified engine. This is what we discussed back in episode 1479, The Speed of Thought, where we saw the industry start to pivot away from just adding more parameters to focusing on how those parameters interact across different senses.
And that brings us to the first major boss fight in this war against latency. You mentioned the memory monster. I assume we are talking about the key value cache? I keep hearing that the KV cache is where dreams of real-time AI go to die.
It really is a monster corn. To understand why, we have to look at how these models actually think. In a transformer model, the KV cache stores the intermediate states of the attention mechanism, so the model does not have to recompute everything for every new token. The problem is that this cache grows linearly with the sequence length. If you are running a model with a context window of 128,000 tokens, which is standard now, a Llama class model can require 320 gigabytes of high bandwidth memory just for the cache. That is more than a single high-end GPU can even hold.
So you are saying the brain is so busy remembering what happened 2 minutes ago that it does not have enough room left to think about what is happening right now? That sounds like a very relatable problem, actually. But 320 gigabytes? That is insane. How are engineers actually shrinking this monster down to size?
There are a few clever tricks that have become industry standards. First, we have grouped query attention, or GQA. In standard multi-head attention, every single query has its own dedicated key and value. It is very precise but incredibly memory heavy. With GQA, multiple queries share the same keys and values. It is a bit like a group of friends sharing one map instead of everyone carrying their own. It reduces the memory footprint significantly, sometimes by a factor of 8, without a massive hit to accuracy.
And then there is paged attention, right? I remember you explaining this to me like virtual memory for AI.
PagedAttention, which was pioneered by the VLLM team, allows the KV cache to be stored in non-contiguous memory blocks. Before this, you had to reserve a giant continuous block of memory for every request, even if the request was short. It was incredibly wasteful, like booking an entire hotel floor just for one guest. Now, we can pack many more requests onto the same hardware because we are only using the memory we actually need, fragmented across the chips.
But wait, Google just dropped TurboQuant today. You mentioned it earlier. If we already have GQA and paged attention, why do we need more quantization? Is this just engineers being obsessive, or is there a real performance gain here?
Oh, it is a massive gain. TurboQuant is a compression framework specifically designed for the newest hardware like the H100 and B200. It reduces the KV cache memory usage by 6 times. But the real kicker is that it speeds up the attention computation by 8 times. It is doing this by using more efficient numerical formats and parallelizing the way the cache is accessed. When you combine that with the Rubin architecture NVIDIA just announced, the bottleneck starts to shift from memory capacity to memory bandwidth. We are finally moving past the limitations we talked about in episode 1555 regarding the failure of batch processing for real-time speech.
Okay, let us talk about the Rubin architecture for a second. Jensen Huang was up there at GTC talking about a 35-fold performance leap over the Hopper architecture. That sounds like a marketing number. Is it actually that fast in the real world?
The leap comes from a few places. The Rubin GPU uses HBM4 memory, which has vastly higher bandwidth than what we saw on the Blackwell or Hopper chips. But the most interesting part of the GTC announcement was the integration of Groq's LPU technology. Groq, which rhymes with Groq, has been the leader in ultra-low latency token generation because their language processing units are designed specifically for the sequential nature of AI inference.
right? Because standard GPUs are great at doing 1,000 things at once, like rendering pixels. But AI inference is often about doing one thing after another very, very quickly. It is the difference between 1,000 people walking slowly and one person sprinting at the speed of sound.
That is a great way to put it. By integrating that LPU style logic into the broader hardware stack, NVIDIA is trying to solve the sequential bottleneck. This is what allows for that sub 100 millisecond response time. When the hardware can generate tokens as fast as a human can perceive them, the interface starts to feel like an extension of your own thought process rather than a tool you are interacting with. It is the speed of light for human-AI interaction.
I want to go back to the software side for a second, because I saw a paper about something called the Saguaro algorithm. It has a very cool name, but it sounds like it is doing something called speculative decoding. Did they just stutter, or is that a real thing?
It is a real thing, and it is a brilliant evolution of a technique we have discussed before. Standard speculative decoding uses a tiny, fast model to guess what the next few tokens will be, and then a big smart model checks those guesses in a single pass. It is much faster than letting the big model do all the work token by token.
Right. The small model is the eager student who shouts out answers, and the big model is the professor who just nods or shakes his head.
The Saguaro algorithm takes this further by parallelizing the drafting and verification stages even more aggressively. It uses multiple draft models or multiple draft paths simultaneously. This is what they call speculative decoding. It is essentially speculative decoding on steroids. In the research published earlier this month, they showed up to a 5-fold speedup over standard autoregressive decoding. But here is the catch. In multimodal settings, this is even harder.
Why is it harder? Is a pixel harder to guess than a word?
This is where multimodal speculative decoding, or MSD, comes in. Text and visual tokens have different levels of entropy. Text is relatively predictable. If I say, the cat sat on the, you can guess the next word is probably mat. But visual tokens are much more chaotic. MSD decouples these tokens in the draft model, processing them separately before the big model verifies them. If you try to guess them together, the visual noise ruins the text predictions.
It feels like we are in this weird arms race where the hardware gets faster, so the software gets more complex, which then requires even faster hardware. But there is a limit, right? We have to talk about the energy constraints. I know you love a good liquid-cooled rack-scale design talk, Herman.
You cannot ignore the physics. The performance per watt has become the hard ceiling for every AI data center on the planet. This is why we are seeing the shift to things like the GB200 NVL72. It is a liquid-cooled rack that treats 72 GPUs as a single massive unit. If we tried to hit these latency targets using traditional air cooling and standard rack designs, the power draw would be unsustainable. We are literally re-engineering the power grid and the cooling infrastructure of our cities just to make sure an AI can answer a question 10 milliseconds faster.
That is the part that always gets me. The sheer amount of physical infrastructure required to make a digital voice sound more human. But let us look at the other side of that. If we do not want to rely on these massive, power-hungry data centers, we have to talk about the edge. I saw that Meta is doing some interesting things with Llama 3.3 and mobile chips.
This is the privacy versus latency debate. If you send your audio and video data to the cloud, you are adding at least 200 milliseconds of round-trip delay just from the speed of light and network routing. That is before the model even starts thinking. If you want true real-time interaction without that lag, the processing has to happen on your device.
And that is where companies like Qualcomm and MediaTek come in. I imagine trying to run a multimodal model on a phone battery is like trying to run a marathon while breathing through a straw.
It is incredibly difficult. But Llama 3.3 has been specifically optimized for these edge chips. They are using extremely aggressive quantization, moving toward 4-bit precision formats like NVFP4. By reducing the precision of the weights, you can fit a much more capable model into the limited memory of a smartphone. The goal is to reach a point where the local model is smart enough to handle 80% of interactions instantly, only calling out to the cloud for the really heavy lifting.
It is like having a quick thinking brain in your hand and a genius level brain in the cloud, and they just hand off tasks to each other seamlessly. But speaking of the cloud, I have to bring up OpenAI's GPT 5.4. They launched it a few weeks ago with that configurable reasoning engine. I actually think that is one of the smartest UI moves I have seen in a long time.
It is a very pragmatic solution to the latency problem. GPT 5.4 has a 1.05 million token context window, which is massive, but it also has native computer use capabilities. As a developer, you can choose the level of reasoning depth you need. If you are just doing a quick voice interaction, you set it to none or low. The model responds instantly because it is skipping the deeper, more computationally expensive reasoning paths. If you needed to solve a complex coding problem, you set it to extra high, and you accept that it might take a few seconds to think.
It is like giving the AI a cup of coffee or a sedative depending on what you need it to do. But it also has native computer use capabilities now, right? That has to add another layer of latency challenges. If the AI is literally watching your screen and moving your cursor, the lag isn't just annoying, it makes the tool unusable.
That brings us back to the synchronization and jitter issue. When an AI is interacting with a live user interface, it has to maintain a constant stream of visual tokens. If there is a hiccup in the network or a spike in compute time, the AI might miss a button click or a window opening. Engineers are now building dedicated jitter buffers and synchronization layers that are more commonly found in high-end video streaming or online gaming than in traditional AI. If that alignment slips by 50 milliseconds, the AI might try to click where a button was instead of where it is.
It is funny how all these different fields of engineering are colliding. We have got game developers, network engineers, and chip designers all working on the same problem. And then there is the emotional side of it. Have you looked at what Hume AI is doing with EVI2?
Alan Cowan and his team at Hume are doing something very special. EVI2 is an empathic voice interface. It is a voice-to-voice foundation model, meaning it does not translate your voice to text first. It listens to the prosody, the tone, and the emotion in your voice directly. They have managed to get the latency down to sub 800 milliseconds for a full empathic response.
Sub 800 milliseconds for something that actually understands how I am feeling. That is faster than some of my relatives, and they are doing it without voice cloning, which I think is a really important ethical distinction. It is not trying to be a specific person, it is just trying to be a responsive, emotionally intelligent interface.
It avoids that uncanny valley where the AI sounds exactly like a human, but reacts with the coldness of a machine. By focusing on the latency and the emotional tone, they make the interaction feel natural even if you know you are talking to a computer. It is a different approach to the war against latency. Instead of just chasing raw speed, they are chasing the speed of empathy.
I like that. But let us get back to the hardcore engineering for a minute. We mentioned the early versus late fusion debate. I want to understand why the data engineering is so much harder for early fusion. If it is just one big stream, why can't we just dump all the data in?
Because you need interleaved data. You can't just train on a billion books and then a billion hours of video. You need data where the text, audio, and video are perfectly synchronized and relevant to each other. This is where the 50 millisecond alignment threshold comes back into play during the training phase. If your training data has a slight lag between the audio and the video, the model learns incorrect correlations. It might think the sound of a door slamming is actually the sound of a person sitting down. The data engineering required to curate and synchronize trillions of multimodal tokens is one of the most underrated challenges in the field right now.
It sounds like we are moving toward a world where the AI is not just a chatbot, but a persistent observer. If it is always on, always listening, and always watching, the engineering challenges move from processing a single prompt to managing a continuous state. How do you keep the KV cache from just exploding if the conversation lasts for 3 hours?
That is where the long context innovations come in. We are seeing things like sliding window attention and memory compressed architectures. Instead of remembering every single detail of a 3-hour conversation with equal clarity, the model uses a hierarchical approach. It keeps a high-resolution cache of the last few minutes and a compressed, lower-resolution summary of the earlier parts. It is very similar to how human memory works.
I was going to say, that sounds exactly like my brain. I remember what I had for breakfast, but I only have a vague summary of what I did 3 weeks ago. It is fascinating to see AI engineering converging on the same solutions that evolution found millions of years ago.
It is a convergence of efficiency. Whether you are a biological brain or a silicon one, you have to manage finite resources to navigate a complex, real-time environment. The difference is that we are trying to do in decades what evolution did over eons, and we are doing it with liquid-cooled GPS and high-bandwidth memory, which I think gives us a bit of an unfair advantage.
Well, let us wrap this up with some practical takeaways for the people out there who are actually building this stuff. If you are a developer in 26 and you are trying to win your own little war against latency, where should you be focusing your energy?
The first thing is to prioritize time to first token, or TTFT, over raw parameter count. A smaller, faster model that starts responding in 50 milliseconds will almost always provide a better user experience than a massive model that takes 2 seconds to think. You have to be ruthless about your latency budget. If you're building a voice app, every millisecond you shave off the TTF, is a millisecond closer to the magic feeling.
And I guess that means choosing the right precision format, too. If you can get away with 4-bit or even 2-bit quantization without losing the core logic of your application, you should do it. Every bit you save is a bit you do not have to move across the memory bus.
That is a huge one. Also, you should be looking at configurable reasoning engines. Do not use the same level of compute for every task. Use a router to decide if a prompt needs the full power of a GPT 5.4 or if it can be handled by a local, quantized llama model. It is about being an architect of compute, not just a consumer of it.
And finally, monitor your performance per watt. Even if you are just a software developer, the cost and the environmental impact of these models are becoming a first-class concern. Efficiency is not just about speed, it is about sustainability.
It is the new hard ceiling. If your application is too power hungry, it will eventually be outcompeted by something leaner and faster. The war against latency is ultimately a war against waste. Waste of time, waste of memory, and waste of energy.
I think that is a great place to leave it. We have covered a lot of ground today, from the memory monster of the KV cache to the liquid-cooled racks of the future. It is a wild time to be watching the industry, especially with the pace of change we have seen just in the last month. The inference king debate is no longer about who has the most parameters, but who can deliver the most intelligence in the shortest amount of time.
It really is. The engineering landscape is shifting under our feet every single week. I am already looking forward to seeing what we will be talking about in April. Will software optimizations like Saguaro continue to win, or will the massive hardware leaps of Vera Rubin settle the debate?
Hopefully we will be talking about it in real time, with sub-10 millisecond latency. Thanks to our producer Hilbert Flumingtop for keeping everything running smoothly behind the scenes.
And a big thanks to Modal for providing the GPU credits that power this show. They are a big part of how we manage to stay on top of these developments.
This has been My Weird Prompts. If you are enjoying the show, a quick review on your podcast app really helps us reach more people who are interested in this kind of deep dive.
You can also find us at myweirdprompts.com for the full archive and all the ways to subscribe.
We will see you next time.
See you then.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow